Okay, so now another distribution that we've seen before is the discrete uniform distribution. So we've seen this in the context of, for example, the distribution of the roll of one six-sided die. That is a discrete uniform. On the set 1, 2, 3, 4, 5, 6. So in general, we suppose we have a random variable u that is uniformly distributed over the set n, which remember we defined as the first n integers. So what that means is the mass function for u is 1 over n for each of the possible values of u. What is the expectation? Well, we could calculate the expectation. Intuitively, we should think of it, it's going to be the midpoint of all the numbers because of symmetry. Okay, so it should be the midpoint, which is n plus 1 over 2 by symmetry. How would we calculate that explicitly? Okay. Well, one way we can do this is clever trick is define delta 2 as the expectation of quantity u plus 1 squared minus expectation of u squared. Okay, why is that relevant? Well, let's just try to calculate the expectation and see. So we calculate the expectation. What do we have? Well, we have a sum over the n values of u. So those values are I plus 1. And we square them, and each one of them has a probability n. And then what we subtract off is expectation of u squared, which is I squared, also divided by n. But what we realize is that what we're going to have on the left here is we have 1 plus 1 is 2 squared, 3 squared, 4 squared, up to n plus 1 squared. And on the right, we have minus the quantity 1 squared minus 2 squared minus 3 squared up to minus n squared. So what we end up with is a telescoping sum. And so what this is equal to is n plus 1 squared over n minus 1 squared over n. So what does that equal? Well, n plus 1 squared is n squared plus 2n plus 1 minus 1 squared. So it's n squared plus 2n divided by n. So we're going to get cancellation. We're going to have n times n plus 2 divided by n. That's n plus 2. Okay. But what we can actually also see, alternatively, is see that, well, expectation of u plus 1 squared minus expectation of u squared, we can actually combine this into a single expectation by reversing the linearity of expectation. But now inside the expectation, what do we have? U plus 1 squared is u squared plus 2u plus 1 minus u squared. So this is equal to expectation of 2u plus 1. This is twice the expectation of u plus 1. And we already calculated this quantity to be n plus 2. So if you put those two together, what you're left with is we have to move some quantities over, but what we're left with is n plus 2 is equal to 2 times the expectation of u plus 1, and therefore expectation of u is equal to n plus 1 over 2. Another thing we observe is from this, the sum of the first n integers we've just derived as n times n plus 1 over 2, which is a useful identity to know. We can use the same method to calculate the variance. And the way that we're going to do it is let's define delta 3 as expectation u plus 1 cubed minus expectation u cubed. Okay, if we do this, what we see, same idea, it's a telescoping sum. We end up with n plus 1 cubed over n minus 1 cubed over n. We end up with n squared plus 3n plus 3. But what we also see, if we look at it a different way, is we bring everything into the expectation. So this is equal to 3. The u cubes are going to cancel. We end up with 3u squared plus 3u plus 1. This is equal to 3 expectation of u squared plus 3 expectation of u plus 1. We already know what the expectation of u is from the previous part. So we get 3 expectation of u squared plus 3 n plus 1 over 2 plus 1. And of course, we already have that it's equal to n squared plus 3n plus 3. So those two parts combined give us one equation, one unknowns, which we solve for to get the expectation of u squared is 1/6 2n squared plus 3n plus 1. Okay. This is equal to n times n plus 1 this is equal to n plus 1 2n plus 1 over 6. And we can note further that the sum from this, the sum of the first n squares is n times n plus 1 times 2n plus 1 divided by 6. So the variance we know how to calculate using the computing formula. variance of u is expectation of u squared minus the square of the expectation. Expectation of u squared, we just calculated. Square of the expectation. That's n plus 1 over 2 quantity squared. We simplify, we get n squared minus 1 over 12. So that is how we deal with discrete uniform distribution between 1 and n. Now, we might not always be specifically interested in discrete and uniform between 1 and n. We might be interested in shifting it a little bit. So there might be a set we might be interested in uniform between 50 and 100. So in this case, we can generalize the distribution and instead suppose W is uniform over A plus 1 up to B, then in this case, what is the expectation of W? What is the variance of W? Well, what we want to do is we want to express, we realize that this spans B minus A plus 1 integers. And the way that we can think about this is let's let U be discrete uniform. So I should say, in this case, we write that U is uniform on N, or discrete uniform on N. And in this case, we're going to be discrete uniform on B minus A plus 1, and write that W is equal to, how do we express W? W is just U shifted over A minus 1. And therefore, expectation of W is expectation of U plus A minus 1. And the variance of W, well, which is equal to B minus A plus 2 over 2 plus A minus 1. And the variance of W equals the variance of U plus A minus 1. Remember that variance is unaffected by shifts, so changes in location. So this is just the variance of U, which is B minus A plus 1 squared minus 1 divided by 12. So that is the discrete uniform distribution, which we've seen in rolling dice and in other applications already.